All right, in this Excel activity, I want to explore the topic of percentiles in general and look at some specific percentiles, namely the quartiles, the 25th, 50th, and 75th percentile. And beyond just calculating those values, what do we use these values for? So in this case, we're going to use the 5-number summary, which is here in the center, made up of the maximum, the minimum, and the first, second, and third quartile. We'll use these values to identify outliers in our data set. So remember, we define an outlier as any number that is above the third quartile by at least 1.5 times the interquartile range, or below the first quartile, again, by at least 1.5 times the interquartile range. So, and we'll get to each of these things one by one. The data we're working with here in column A is 40 values. These are recorded levels of cotinine in cigarette smokers. Okay, so first thing I want to do here is determine the 5-number summary. And I want to do this 2 different ways. One, using the method presented in the textbook, and then 2, using the built-in Excel functions. And then we'll use this 5-number summary to construct both a box plot and a modified box plot. Well, actually, we can't do the modified box plot without first answering number 2. Okay, so 5-number summary. The method in the textbook, the one I'm going to be using is using this flow chart here. Now again, different textbooks offer different methods for finding percentiles and quartiles. It's one of the things that makes this topic a little confusing, is that there is no one formula for percentile. So for example, if you pick up 10 statistics books, all of them will have the same formula for mean and standard deviation and variance and coefficient of variation, correlation coefficient, all these other statistical metrics, except for percentiles. So different books offer different formulas. Not too many different formulas, but there's 2 or 3 different formulas for calculating percentiles by hand. So this is the method from the book that I'm using currently. If your book presents a different method, then just ignore the book method I'm using. So here in yellow, I'll use the textbook method, so basically manual calculations, and in blue, I'll use the Excel formulas. Now you'll see over here, for Q1, Q2, and Q3, I have 2 blue boxes. Well, I'm going to, there's 2 different ways we could do this on Excel, and I want to make sure you're aware of both methods. So the minimum value is the smallest value in the set. So so in yellow, I'm not using any Excel functions. I could use Excel just for basic calculations, plus, minus, times, and divide. So the minimum value, I go over here, I look at my data set. The minimum value is 1, and the maximum value, if I scroll to the bottom, the maximum value is 551. Okay, so minimum and maximum are pretty easy to do. 551. And the second quartile, this is equal to the median of the set. So the median is the middle value. So if there's 40 values in the set, well, the first half is 20 and the second half is 20. So the median will be halfway between the 20th and the 21st values. And in this case, you see they're both 173. So median value, which is the second quartile, is 173. So now for the first quartile, so again, this is, let me actually copy this over. Oh, it doesn't do the subscript. Okay, well, the first quartile is also the 25th percentile. And the third quartile is also the 75th percentile. Okay, so we'll use the textbook method to calculate the 25th and the 75th percentile. So according to this flow chart, okay, we first arrange the data set in order and then calculate this value L, which is, if we want the K percentile, we'll do K over 100 times N. So in this case, we want the 25th percentile. So what this K over 100, so this part here, what we're actually doing is, if we want the 25th percentile, we want what's 25% of the set. So this K over 100, what we're actually doing is 0.25 for the 25th percentile times the size of the set N. We'll use the size of the set, which is, in this case, 40. So 25% of 40 gives us 10. Okay, so at this step, we get 10. Now next, we say, okay, well, is this number we just calculated, is this a whole number? So now this is the question. Is it a whole number, yes or no? The answer is yes, so we're over here. So the 25th percentile, according to this, is halfway between location 10, since we got 10 in the previous step. So halfway between location 10 and 11. So what we're going to get here is the average of positions 10 and 11. Positions 10 and 11. Excuse my handwriting, it's a little difficult to write on my computer screen. Okay, so according to this flowchart, we arrange our data in order. We calculate, in this case, 25% of the set. So that would be 10 values. Since 10 is a whole number, we're over here. And our 25th percentile would be the average of positions 10 and 11, or halfway between positions 10 and 11. Okay, so doing this manually, so here's position 10, and here's position 10, and here's position 11, and we want the average of these two. So to take the average, we add them up. So that'll be 87 plus 103, and divide by 2. Okay, so according to the textbook method, our 25th percentile is 95. 75th percentile, we'll do the same thing. Instead of 25%, we'll use 75%. So that will give us, let's do this, so 0.75 times 40, or 75% of our set, will give us 30. Okay, so this gives us 30. So again, 30 is a whole number. So question, is it a whole number? Yes, we're back over here. So we take the average of positions 30 and 31. So instead of using 10, we'll use the 30. Instead of using 11, we'll use the 31. So halfway between 30 and 31. So now we're Now we're down here, positions 30 and 31. Oop. Let's do that. Okay, so the average of 253 and 265. We could say equal 253 plus 265 and divide that by 2 to find the average. Okay, so this is our 5-number summary on Excel, and then the interquartile range. Remember, interquartile range is equal to Q3 minus Q1, so the distance between the third and the first quartile. So that will be equal to the 259 minus the 95. So interquartile range, I get 164. Remember, I'm using Excel, but I'm really doing these calculations manually. I would not recommend using Excel in this manner. This is sort of just to give you an idea of another method. This is sort of the paper and pencil method presented in the textbook. On Excel, let's go through and do the 5-number summary again. So the minimum value, the Excel function is minimum. And all of our data is in column A. So we're using everything in column A. So instead of typing A1 through A40, I could just click on the A. So I'm using everything in column A in my calculations. So the minimum of column A, there's our 1. The maximum of column A equal max, hit the A, and there's our maximum. Now, for the first quartile, we could do this one of two ways, because we have Q1 or we have P25. They both mean the same thing. So I'll use the quartile function. Again, I'm using always the inclusive quartile function. And the array, that's our data. So I'll say column A and comma. And now Excel pops up a list. Which quartile do I want? I'll type 1 for first quartile. Okay, so 99. Again, Excel and the textbook method will give us similar but different answers. Q2 is the median, so we could use median, we could use second quartile, we could use 25th percentile. So actually, let me just put that in here. Second quartile is the median. So we have a function for median. So that's equal median, and data is in column A. So there's only one definition for median. So any method you use, the second quartile is always going to give you the same result under any method. So here I use the quartile method. I could use percentiles. So there's also a percentile function, equal percentile, and I'm using inclusive. Our data array is column A, and I want the 25th percentile, so 25% is 0.25. So in these two blue cells, these will always give me the same exact result, because the 25th percentile is the first quartile, and so on. So if you wanted to, you could use 50th percentile. For median, again, I would recommend median because it's just a faster process. 50th percentile, so 0.50. And for the third quartile, again, I could use either the quartile function, column A, and 3 for third quartile. You could just click on the 3 down here. So third quartile, or 75th percentile. So our array of data is, again, column A, And 75th percentile is 75% or 0.75. Okay, so whether we're using the quartile function or the percentile function doesn't matter. We're going to get the same result. Our interquartile range is equal to Q3 minus Q1. So it's similar to what we got from the textbook, but not exactly the same. So now, when we're, before I do the box plots, let's look at number 2. Are there any outliers in the set? If so, highlight them. So we define an outlier as this. So these cells right here, let me put this here in green. This is the definition of outliers. So anything below Q1 minus 1.5 times IQR. So 1.5 of the interquartile range below the first quartile, that's the low end, and anything below that is an outlier, or 1.5 of the interquartile range above Q3 would be the high end. Anything above that would be an outlier. So we'll say equal Q1, which is 95, minus 1.5 times the interquartile range, which is 164. Now again, in yellow, I'm doing everything manually. In blue, I'm going to use a quicker method using the Excel functions. So Q3 is 259, and we're going to add 1.5 times the interquartile range, which is 164. Okay, so anything below negative 151, of which there are no values, and anything above 505, of which there are 2 values. So there are 2 outliers in this set, according to the textbook method. And if we're using Excel, I'll say equal Q1 minus 1.5 times interquartile range. And for the upper boundary, I'll say equal Q3 plus 1.5 times the interquartile range. And again, I get the same result in terms of identifying outliers. Anything above 491.5, and again, the same 2 numbers are above 491.5. So the individual values, there's going to be a little deviation here, but in terms of identifying outliers, whether we're using the manual method from the textbook or the Excel functions, we still identify the same 2 outliers. So now, the third question, calculate the mean and the median of both sets, the mean and the median both with the outliers and without, and make note of which measure of center is more affected by removing outliers. So for the mean is equal average. So the mean of the set, we're using all of the data in column A. The mean is 187.6. And the median, using all of the numbers in column A, 173. Now, when we remove the outliers, let's see what happens. So equal mean, we have 40 numbers. I'm removing the bottom 2. So we'll just go A1 up through A38. So that will catch the first, that will basically catch all the non-outlying numbers. So, ooh, what happened here? Oh, sorry, mean is not the function, average. Equal average, A1 through A38. So the mean differs by almost 20 points with and without the outliers. And the median, again, we'll use A1 up through A38. The median, it changes, but not nearly as much as the mean changes. So when we say the mean is affected strongly by outliers, the median is resistant to outliers. Resistant doesn't mean it doesn't change at all, it just means it changes very little. Okay, I'm going to hold off on the box plots till the end because I have to draw those by hand. So now let's go down here and calculate these percentiles and the percentile value for x. So in these two boxes for P20 and P85, we're doing the same thing we did up here. So for the 20th percentile, we want 20% of the data set. So let's get rid of this. Actually, let's get rid of all of this. Okay, so 20% of, so right now we're here. Arrange the data in order, done. Now we're here. Compute the k% of the size of the sample. In this case, the k is 20. So what's 20% of 40? That would be exactly 8. So here we get the number 8. So 0.2 times 40. So is this result a whole number? Yes. So we're over here. So we take the average of positions 8 and 9. Okay, so we need the average of these two numbers, and our 20th percentile will be we'll say equal, and manually to take the average, that's 48 plus 86, and divide that by 2. Using Excel to calculate the 20th percentile, we'll say equal percentile inclusive, and our data is column A. We want the 20th percentile, so 0.20. 78.4. Again, things work a little quicker, a little smoother, sometimes considerably quicker, considerably smoother when we're using Excel. So now for the 85th percentile, we want 85% of 40. And let's see. What is 85% of 40? Actually, this might be a problem. That gives us also a whole number. You know what? I'm going to change that so you can just see both methods. Instead of 85%, I'm going to change that to 88%. I want the 88th percentile. So 88% of 40. That gives us 35.2. Okay, so now data is arranged in order. We calculate, in this case, 88% of 40. We get the number 35.2. And is that a whole number? No. So now we're down here. Now we're down here. So change L by rounding up to the next largest whole number. So always round up. So that will give us position 36. So the percentile we're looking for is the number in position 36. So let's turn the pin off. So position 36, this is what we're looking for, and that's the 290. So manually, the 88th percentile giving us 290. If we're using Excel, again, equal percentile inclusive. Our data is column A, and we want the 88th percentile. So in this case, very, very close, 289.32 versus 290. Again, this textbook method, this is a very basic, was one of the simpler textbook methods I've seen. Other books use what's called interpolation. It's another method. I'm going to stick with this one. And again, if you're using a textbook that does not use this method, maybe focus only on the Excel side of things. Okay, so now the other direction, instead of starting with a percentage and you finding the location, let's start with the location and find the percentile. So I want the percentile that corresponds to the number 115 in the data set. So 115, where is 115? 115 is over here. So 115 is in position 13. So we're basically converting this to a percentage. And the definition of percent is, well, basically a percentage. And this is not a statistics definition. This is a general mathematical definition. A percentage is part of a whole. So part divided by whole. So what part of the set is below 115? So if we look at this, 115 is in position 13. So let's switch to a different color here. This is the part of the set below 115. So there's 12 numbers. So when we go over here, our percentile is equal to the part of the set below 115, which is 12, and divide that by the whole set, or the size of the set, which is 40. So to convert 115 to a percentile, just 12 divided by 40. And we can convert this number to a percentage up here, and let's do this. So 30%. And we could even clean it up a bit, get rid of the decimal points. So the percentile value for 115 is the 30% or 30th percentile. Okay. And the last thing to do is to construct the box plots. And the box plots we're going to use, I'll use the Excel numbers, so I'll use this 5-number summary, and when we're constructing a box plot, that's all we need. We just need these 5 numbers. When we're constructing a modified box plot, we're going to basically take these 2 guys out, then construct the box plot, and we'll label those 2 outliers with usually a dot on the graph or an asterisk, something like that. Okay, so let me actually, I'll move this out of the way, and I'll construct the box plot right over here. So box plot's a very basic graphic. It's a one-dimensional graph. So our minimum value is 1. Our maximum value is 551. So the box plot consists of a horizontal line or a vertical line. You could draw them horizontal or vertically, connecting the minimum to Q1. So our first quartile is 99. Our median value is 173. And our third quartile is 256. Okay, so our box plot would be basically a line connecting minimum to first quartile. Then we have a box around the interquartile range. Hence the name box plot. And another line connecting Q3 to our maximum value with a vertical bar over the median. So that's it. There's our box plot. Now, if we wanted to make a modified box plot, which I'll do in blue, the only difference is we are taking away the outlying values, so our box plot will end at 477 rather than 551. So let me put in the 477, maybe about right here. Maybe not drawn perfectly to scale. 477. So our modified box plot would look something like this. Same minimum, first quartile, median, third quartile, but our maximum would now be stopping at, sometimes you see a little hash mark there, stopping at 477. And in a modified box plot, we use, normally some symbol to represent that there are outliers, so either a little star, asterisk, a little dot. So this set has 2 outliers, one there and one there. Okay, so the black box plot on bottom is the regular box plot. The blue one on top is the modified box plot. I'm going to skip this one question about does the data appear to be skewed? And I'm going to say I'm skipping this because my box plot is a very rough sketch. It's not drawn to scale. You really need a nicely drawn box plot to really identify the skewness in the set. So I'm going to leave it at this. We covered a lot of things here. 5-number summary, interquartile range, using the interquartile range and the 5-number summary to identify outliers, and visualizing the 5-number summary with and without the outliers, and then calculating a couple of percentiles down here. And finally, we looked at 2 measures of center, mean and median, and how they are affected by the removal of an outlier. The mean was affected about 600% more than the median was, so about 6 times more. Okay, so that's it for this one. I hope this helps.